Now, it should ideally finish the material that is on that test. That leaves us in an awkward spot as far as Wednesday goes, because we still have empirical formula, molar mass of compounds, percent composition, that kind of things that we need to be covering. But I think we've had enough material for a test without piling that in on top of it. And so what we're going to do is, where we finish today, that will be the end of exam 2 material. And what we talk about on Wednesday will actually be exam 3 material. But that keeps us from either having the exam on Wednesday, which nobody wants, including me, and the other possibility of having that material as well as all the quantum numbers and all the electron configuration and the light equations and all of that into one massive test. Right? So it's not ideal, but I think it's the best of our 3 options. So just know that test 2 material ends today, even though the exam is a week from today. First thing we're going to go over today is these properties. We talked about these last time, right? Thought we did. We didn't define these at all last time? Oh. Oops. Okay. All right. Did we talk about covalent, ionic, and metallic bonding?
No.
No.
Wait.
Covalent, ionic, and metallic bonding?
No.
I forgot. I guess I'm getting the Tuesday, Thursday blurred with Monday, Wednesday. I'm sorry. You have a page like this in the notes. And it's blank. That's what I was afraid of. All right. That's where we'll start. When elements form compounds, it's the result of some kind of bonding going on, chemical bonding that attaches them to each other and therefore changes the properties of those elements so that you have a new material that behaves in entirely different ways. There's 3 kinds of bonding, but that really derives out of 2 kinds of elements. Those 2 kinds of elements being nonmetals and metals. And for the most part, your pattern on the periodic table was that zigzag line that goes between boron and aluminum and winds its way on down. Everything to the right of that zigzag is nonmetal, everything to the left of that zigzag is metal, with the exception of one, and that one is hydrogen. 9 times out of 10, if I ask you what element is the exception, it's going to be hydrogen. Because hydrogen's an exception to most things. So hydrogen, even though it's over to the left, it really is a non-metal. And as much as it fits properties, to whatever degree it fits the non-metal patterns best. Now, Defining characteristics of metals and nonmetals. There's some properties about metals and nonmetals that you do already know about. For example, metals are very good at conducting electricity, and nonmetals don't. And metals are good at conducting heat, and nonmetals don't. Nonmetals are considered insulators, but metals are really good conductors. And there's other properties we could list, but we won't. The important thing here is that those conductivity properties, as well as a whole lot more of their properties, all derive from one fundamental property, and that's that metals have a weak attraction for electrons. When atoms come together to bond and form compounds, it's the electrons that get involved in that bonding, and how they behave is a result of what kind of element you're dealing with. So to start, let's say we're bonding a metal with a non-metal. Here's the metal atom. There's the electron in orbit. And there's only a small amount of force, positive, negative force, that keeps that electron in orbit. But for the nonmetal, with its electrons, you got a lot of force. There's a lot of attraction to that nucleus. Now, I don't know a good way to draw force, and so I'm drawing in dotted lines. And the more dotted it is, the stronger it is, all right? So the electron that I'm showing on the nonmetal is rather firmly bound in orbit to that nucleus, but not so much on the metal. And so if you take the little orange atom and you rub it up against the purple atom, and you let these electrons do what they're going to do, which is orbit, then when this electron goes around in orbit and gets to right about here, then all of a sudden it feels attraction to both nuclei. Does it feel equal attraction to both nuclei? No, it feels a whole lot more toward the nonmetal atom than it does to its own nucleus, correct? And as a result of that, since the force is so much more strong in this direction, then that electron gets stripped away, starts to orbit the nonmetal now, and now you've got an anion, because this nonmetal has more negatives than positives, and the metal has become a cation. Cation, anion, this is ionic bonding. It is almost always metal to nonmetal bonding. Almost always. And functionally what occurs that makes this work is transfer of an electron from metal to nonmetal. Which forms your ions. And so now you've got these particles that have definite positive and negative charges to them, and they all cluster up as a crystal, as an alternating array of charges. All the little positives are going to be surrounded by negatives, and all the negatives are surrounded by positives in a three-dimensional crystal there. And what you've got holding those ions together is simply opposite charge attraction. It's rather similar to taking magnets and putting them up to where they align in opposite charge. This is electrical and not magnetic, so it's not the same, but it's a similar type thing. And it results from transfer of electrons. The electron leaves the metal, goes to the nonmetal, and stays there. And that's what generates the ions, hence the term ionic. When you're bonding metals to nonmetals, that's the way it's going to work. And the reason that happens is that disparity in attractive force. Do you see that? Nonmetal has a strong attraction, not only for its own electrons, but everybody else's electrons too. And it'll take them if it can. And in competition with a metal, it can. And that's how you generate those ions. That's the way ionic bonding works. Now next would be if we have two nonmetals. So here's a nucleus, here's the electron, here's the other nucleus, here's the other electron. They're both nonmetals. They both have a significant amount of force exerted on their electrons. Same situation though, these electrons are orbiting, so this electron, as it goes around in orbit, it gets to a position right about here. All of a sudden, it feels strong attraction toward both. And here's the key question. Can the atom on the right strip that electron away like it did over on the other board?
No.
Why not?
Because it's the same force.
Because you've got comparable force, right? Now, it's not that it's not trying to. It is trying to. But this other non-metal is more able to put up a fight. And so not only do they end up in a perpetual tug-of-war fighting over that electron, but this one comes around in orbit and gets caught in there too. And so what happens with non-metals bonding is you end up with, this is what your book calls sharing. Sharing of electron pairs. It's always pairs, because what you've got is each atom is trying to steal an electron from the other atom. And so you're caught in that perpetual tug-of-war, where each is trying to pull one away from the other. Like I said, it's called sharing, but it's really not as polite as sharing would be. All right, it's much more of a competition. It's just that neither one is able to win. Neither one is able to snatch the one away, and you get caught perpetually in that situation. Go ahead.
And so a non-metal is going to win the electron because it's stronger.
Yes.
Okay.
But in this situation, where they're both rather strong, neither one is going to truly win, because neither one is completely able to strip the other one away. Does that make sense? Do you see the difference? Okay, go ahead.
You said that ionic is like almost always metal and a non-metal, but like can one of the non-metals and this, and they like steal it? Because doesn't one have more like because there's like negative and like don't one like steal it for longer or something?
For longer?
Yeah, can't.
Yeah, I mean, you still end up with the pair being shared. Okay, if you're going to put numbers to it, if this, let's say that if this were chlorine and chlorine, where the pull was exactly equal, then that would be perfectly 50-50 sharing. Okay? But when we're talking about over here with ionic, This is 0 and 100%, okay? But now with what, I think what you're saying is if you have different nonmetals here, let's say it's sulfur and chlorine, then that's not exactly equal. One of them will have a little bit more pull, and maybe it's 60-40 as opposed to 50-50, okay? It's still shared, but it doesn't, just because it's shared doesn't mean it's shared 50-50.
What is ionic bonding thing besides a metal and aluminum? You said it was almost always, so.
Can I have about 20 minutes before I answer that? Okay. Is this kind of what you were asking about?
Yeah.
Okay.
I just didn't know if maybe like this could become ionic because you'd say almost always.
Well, let's go ahead and answer that. The almost always thing is this. Most of your cations are metals of one sort or another. But there's a few cations, especially this one, that even though this is nitrogen and hydrogen, that's entirely non-metal, it's a special case of a polyatomic cation. And so ammonium is a positive charge. And so the ammonium ion and the chloride ion, that's ionic bonding, even though it's non-metal, non-metal, non-metal. So the special case, the reason I said almost always, let's just go ahead and fix it now, I guess. Ionic bonding is either metal with non-metal or ammonium with non-metal. Is that better? Okay. So metal or ammonium with non-metals are going to be the ionic type. This is called covalent bonding. And you see how it plays out differently than ionic. But do you see that the driving force behind both of these bonding types is exactly the same? The driving force being non-metals' tendency to gain electrons. If it's in a situation where they can steal one outright, it becomes ionic. If it's not in that situation where it can steal one outright, you get caught in this sharing. But the driving force is the same in both. All right, third type. And this is when you're bonding metals with metals, called metallic bonding. Not the most creative name, but it's definitely descriptive, because that's who's involved. And the way this works, here's the two atoms. We're going to focus on the same electron on the left like we did before. Each atom has some valence electrons, not much force restraining those electrons. And so when this electron comes around in orbit and gets to here, it feels some force to its own nucleus, it feels some force toward the other nucleus, but not much force toward either. It's not that the other atom is trying to steal it away. There's not much force there at all. So it just kind of drifts. And maybe it'll stay over here, or maybe it'll wander over there. And maybe it'll stay over there for a while, and then it'll go back. What you have with metallic bonding is a perpetual exchange of electrons. Constantly going here and there, and here and there, and here and there, and here and there. Not in any particular location on any particular atom. The term here is delocalized. Delocalized means not in one fixed location. You cannot pin down one electron and say, this electron is on this atom. Because they're just in flux. Two atoms. So if these are atoms of a metal, let's say this is a copper wire. And we'll focus in on this electron right here. This is a copper wire laying on the bench top. You're not doing anything to it at all. It's just laying there. Trick question. Where's the orange electron? And if you say center atom of the bottom row, you're wrong. Anybody for everywhere? Go ahead. Question?
No, I was going to say it's everywhere.
Yeah. It's here for a little while, then it's here for a little while, then it's over here for a little while, etc. That electron and all of those other valence electrons, they're all in flux. These are free-range electrons. They're just moving everywhere everywhere available within that wire. They are already in movement when you're not doing a thing to it. They're already in movement, and it's that perpetual exchange that holds the atoms in contact with each other. And that results from this very weak attraction that lets them drift from one atom to another. Do you see that? So then, that's what makes it rather easy for you to hook up this wire to something and start shoving more electrons in one end of the wire. When you start sending electrons in one end of the wire, what's going to happen? Electrons are going to squirt out the other end of the wire. That's electrical conductivity. That's the reason metals conduct electricity so well, is those electrons are already flowing. So you shove water in one end of a hose, it has to come out the other, correct? You shove electrons in one end of the wire, they're going to come out the other. And that sets up a coherent flow because these electrons are already motion. It doesn't take much of a nudge, voltage-wise, to set up a coherent flow. The reason metals are good at carrying electrical current is because they have these delocalized electrons already. And the reason they have delocalized electrons already is that very, very weak force that's holding them in orbit. Do you see how conductivity derives from this? If that had been a fiber of a nonmetal, and you started to put electrons in one end, would those flow through the other end? No, because nonmetals are greedy. They're going to keep the electrons. Those very first few atoms would grab them and keep them, and there'd be no flow whatsoever. That's why nonmetals are considered insulators, electrical insulators. They're not going to flow. They're not going to freely pass electrons down to their neighbors. They grab them, they keep them, and that's the end of it. Go ahead.
How about if they get more than they need?
More than... You mean like adding on to make them negative?
Mm-hmm.
That's extremely difficult with a metal. They're going to ditch them somehow. It's very hard to make an electron, an extra electron add on to a metal. They'll pass it off to somebody else, if there's anything else around. Question? Did you have a question?
I was just gonna say, with the exception of hydrogen, it's still +2, correct?
Well, hydrogen's not a metal.
Right.
So yeah, this does not apply to hydrogen. This just applies to metals. Other question? All right. Now there's more properties that we're going to define and talk about now. But if you're okay with the metals having a weak attraction, non-metals having a strong attraction, then you already know how these properties are going to play out. Once we define them, you ought to be able to predict them with no difficulty. Electronegativity. And I'm going to define this with 2 lines. First of all, the literal one, I guess, the tendency to become electrically negative, that's where electronegativity comes from. Just the word itself comes from electrically negative. And the way you become electrically negative is by gaining electrons. Tendency to become electrically negative, tendency to gain electrons through bonding. Through bonding meaning in direct competition with another element. Now, based on what we just said about metals and non-metals, who's going to be better at this? Non-metals. Because they have that stronger attraction, correct? And they tend to form anions, correct, by gaining electrons. They routinely form anions. Anions are negative, and that resulted from that strong attraction that we talked about. So the pattern here is non-metals have high electronegativity. I'm just going to abbreviate this, EN for electronegativity. Non-metals have a high electronegativity. They have a high tendency toward gaining electrons. And of your non-metals, fluorine is the highest. Fluorine needs to be a reference point for you. Because when we go through all these properties, if you remember what fluorine is like, it enables you to predict what these others are going to be like. And in using fluorine as our reference point, we're kind of disregarding the noble gases, which is fine because they don't react and form compounds anyway. That was that octet rule thing from before. They have the full octet, they have no tendency to gain or lose, they're not reactive elements. So in setting our reference points, if we don't include the noble gases because they're unreactive, and we don't include hydrogen because it's weird, then that leaves fluorine as the top right corner of the periodic table, and fluorine is going to be your reference point. Fluorine is the most reactive nonmetal. It has the highest electronegativity of your reactive elements. And so by omitting those, fluorine is clearly the reference point. You want to memorize these definitions, but you also want to memorize what fluorine is like in behavior. Because then other elements on the chart, based on proximity, are going to be more fluorine-like. For example, if we were comparing chlorine and bromine in terms of electronegativity, Chlorine has a higher electronegativity than bromine does. And how do you know that? By proximity to where fluorine is on the chart. The closer the symbols are to fluorine on the chart, the more similar they are to fluorine in structure and behavior. And part of being fluorine-like is having a high electronegativity. So chlorine has a higher electronegativity than bromine. Bromine has a higher electronegativity than iodine. Bromine has a higher electronegativity than selenium. It's all proximity based. Your patterns can be read from the chart based on the fluorine reference point. Ionization energy. This is defined as the energy required to remove an electron from the isolated gas phase atom. A bit of a context difference here. When we were talking about electronegativity, we were talking about bonding. You had a couple of elements in direct competition fighting over the electrons. With ionization energy, that's not the case. You've got one element, you put it in a box, you heat it up to vaporize it so it's all gas phase, and then you start poking at it with a laser. And you zap it, trying to knock an electron loose. If it doesn't work, you crank up the voltage and you zap it again. And you keep going higher and higher and higher until you knock an electron loose. So I guess, equation-wise, if this is our element, we're putting in energy in order to remove an electron from that atom, and when that atom loses the electron, it becomes a cation, correct? Is that process going to be easier for a metal or a non-metal? Is this process going to be easier for a metal or a non-metal? Who's better at forming cations? Metals. Metals form positives routinely, correct? That's going to be easier for metal. So metals, that's not going to take a lot of energy for a metal. But non-metals are going to fight you for that electron, because non-metals want, not only do they want to keep what they've got, but they'd like to gain more. Stripping one away is going to be difficult. Non-metals have very high ionization energies. And fluorine is the highest. Of your reactive elements, fluorine has the highest ionization energy. Is the most resistant toward forming that cation. Question about ionization energy. Bromine or iodine? Which one has the higher ionization energy? Bromine. Sulfur or chlorine? Which has the higher ionization energy? Chlorine.